Hey everyone, it's Hazel and welcome back to another ACE Explains video. Today I'm going to be teaching you guys how to balance nuclear reactions. This is very different from balancing chemical reactions, which I'm sure that you've learned about or have seen our video about. But yeah, today we're going to be balancing nuclear reactions, and the big thing about nuclear reactions that makes it different is that all the products emitted from a nuclear reaction are one of the 4 types of nuclear radiation. If you don't remember the 4 types of nuclear radiation, I have a video on that, so don't even worry about it, and the video will be linked in the corner and also in the playlist below. Okay, let's get started. So let's say we have a question similar to this one where it says, radon is a radioactive gas formed in the soil, and it can cause lung cancers when inhaled in high concentrations for a long period of time. Write a balanced nuclear reaction for the decay of radon-222, which emits an alpha particle. Okay, the first part that is the most important is to decide what information is important to you as you're solving this problem. So, important information would be something like, we're dealing with radon, and we want a balanced nuclear equation for the decay of radon, which means we're going to be turning radon into 2 other things. So radon is the reactant, and alpha particle and something else is the product. So radon is being broken down, decay, and it emits an alpha particle. So the first and most important thing to start with is to start with building the isotope radon-222. So this isotope has a mass number of 222. Actually, I don't like the way I wrote that. Yeah, but it has a mass number of 222, right? That's the isotope. However, in an isotope, we need to know both the mass number and the atomic number. So we're gonna take a little trip over to the periodic table, which I have right here, and we're going to look for radon. Now, radon is, I think that's radium. Radon, here it is. Radon is right here. I'm very carefully gonna box it in so you guys can see. And radon has an atomic number of 86. The atomic number is the big number located on top of the atomic symbol. So we know that the atomic number of radon is 86. Atomic number. Okay, perfect. So now we are going to build this isotope. Remember, an isotope looks like this. We have the mass number on top and the atomic number on the bottom. And then we put the symbol right here. So we have the mass number on top, 222. We have the isotope on the bottom, the atomic number on the bottom, which is 86. And then we have the symbol for radon, which is Rn. That is our sole reactant. Remember, we are solving or writing a balanced nuclear equation for the decay of radon. So our sole reactant, which is on the left side, is radon. Our products will be one element or one isotope and an alpha particle. The common system, or I shouldn't even say common system, the proper way to write a nuclear equation is reactants on the left, products on the right. Right? This is for any equation. So a chemical equation or a nuclear one. The difference is with a nuclear equation, it's going to be products plus an emitted nuclear radiation. In this case, an alpha particle. Okay, so radon has an alpha particle, or it emits an alpha particle. So we're gonna start with what we do know, which is the alpha particle. Remember, an alpha particle can be written as a helium isotope with a mass number of 4 and an atomic number of 2. So that's how I'm gonna write it here. And then I'm gonna put addition, and then we're going to figure out what is gonna go on the other side. Well, I'm gonna start with the atomic number since it's the easiest. We know that we have a 2 here and we have an 86 here. So it's something plus 2 equals 86, right? So something plus 2 that equals 86, right? So it's almost like we're going backwards a little bit. We're acting to the left instead of to the right. That something is going to be 84. So we know that whatever element we choose, it has a mass number of 84. 84, okay? We also now need to solve for the atomic number. I'm sorry, we just solved for the atomic number. We now need to solve for the mass number. So we're thinking it's something plus 4 equals 22, right? Something plus 4 that equals 222. That something is 218. So our mass number, our mystery mass number is 218. Basically, we need to now look for an element that has an atomic number of 84. We always lead with the atomic number because remember, an isotope can have any mass number, but it's gotta have a specific atomic number that matches it to an element. An element can have any number of neutrons, but it's gonna have a specific number of protons every single time. So we're gonna go back to the periodic table and we're gonna find the element that has an atomic number of 84. If I look here, I see that the element that has an atomic number of 84 is polonium, right there. So it is going to be a polonium isotope. And we just write the element symbol since we already have the mass number and the atomic number. So radon-222 emits an A particle and also produces a polonium isotope, polonium-218. Okay, awesome. So now we're gonna do the next question. Write a balanced equation to show how this nucleus decays to form an alpha particle, and it is polonium-218. Don't make the mistake of assuming that this polonium-218 nuclear equation is going to be similar to the one we just did. It's actually going to be a little bit different. So we know that we are trying to find a nucleus that decays to form an alpha particle. This nucleus being polonium-218. I think that's like super important and people might not catch that. So we're going to start with polonium-218 as our reactant. We know that one of the products is an alpha particle, right? Because it decays to form an alpha particle. So we are going to add first the alpha particle, also known as the helium atom, and then we're going to add the other product, right? So thinking in terms of addition, we know that this mystery product is going to have an atomic number of 82, since 82 plus 2 equals 84. We also know that it's going to have a mass number of 214, since 214 plus 4 equals 218. If we go over to the periodic table, which I have right there, and we look for an element that has a mass number of 82, an atomic number of 82, we get lead or antimony. So let's go over here. Lead's element symbol is Pb. So when polonium-218 decays, it emits an alpha particle and also results in the product lead-214. Yay! Okay, now I'm gonna give you just a couple of seconds to try. Actually, I don't want you to try this one because this is beta emission. So you've never done beta emission before. So let's do it together. Okay, write a balanced nuclear equation for the beta emission of iodine-131. You might be asking, how did I know that this was beta emission? Well, I just looked at the Greek number. So the first two that we've been doing have been alpha, and that's because I looked at the Greek letter and it's the A symbol. So this B symbol is for beta. So we're going to be emitting a beta particle in this one. So iodine 131, we know that that means that iodine has a mass number of 131. Just a quick glance at the periodic table to refresh my memory. Iodine has an atomic number of 53. Right there, 53. So we put a 53 as the atomic number. Let's start with what we do know, which is that iodine 131 emits a beta particle. So the correct terminology for a beta particle, or the correct way of drawing a beta particle, is to give it a 0 mass, a -1 atomic number, and to write an E, just like that, to show that it is an electron. Then we add our product. Well, whatever goes here has to subtract by 1 to equal 53. Right? So I'm thinking something minus 1 equals 53. So that's obviously going to be a 54. So our atomic number is going to be 54. Same thing, whatever goes here has to add to 0 to equal 131. That's not super hard. It will end up being 131, because 131 plus 0 is 131. Don't know why on this side my arrows are super wonky. Okay, so we know that the atomic number is 54 and the mass number is 131. When we go to the periodic table, we're looking at the atomic number only, since any isotope can have any mass number, but it's got to have a specific atomic number to show what element it belongs to. So I'm just gonna go to the periodic table, and we are right here. This element has an atomic number of 54. It is xenon. So we go back to our question, and I put the element symbol for xenon, which is Xe. So iodine 131 emits a beta particle and also results in the product xenon 131. Okay. This one is positron emission. So write a balanced equation for the positron emission of arsenic 74. So that means this time we're going to be forming a nuclear reaction that emits a positron, which, if you remember from my last video, is the antiparticle to the beta particle, right? If that gives you a clue. So arsenic has a mass number of 74. And it also has an atomic number of 33. So 74 on the top, 33 on the bottom, and that is the arsenic isotope. Okay, we know that it emits a positron, okay? That's the most important part, is to remember that it emits a positron. So, I just blanked for a second there. Okay, positron has a 0 mass and a +1 atomic number, and is represented with an E as well. So, this is a positron. Now, when we are solving to figure out what our missing product is, our missing isotope, we have to think in math terms. Whatever the atomic number is going to add to 1 to equal 33, right? So something plus 1 equals 33. 32, you guessed it. So the atomic number of this mystery isotope is 32. Same thing, same concept. The mass number is gonna add to 0 to equal 74. Obviously, that means that the mass number will be 74. There you go, 74. So thinking about now, what is the element symbol for this isotope? We go back to the periodic table and we look for the element that has the atomic number 32. And that is right here, that is germanium. Oop. Oh my gosh, it just froze on me. Germanium, right there. It's all messy. There we go. That is germanium, and its element symbol is just a simple GE. Ah! Okay, this is so exciting. I love when I like get things. Well, not that I get things, but I love when I help people get things. So I have some practice questions for you all, and this time they are not word problems. They are simply nuclear equations that are missing parts. So look at this one. We have an isotope of rubidium, rubidium-77, which reacts to form an unknown product and a positron particle or positron emission. Okay, I'm gonna give you a few minutes to try this one on your own. Awesome, ready to go? Okay, let's dive in. So rubidium-77 has a mass number of 77 and an atomic number of 37. We know that it emits some sort of mystery product and also positron emission. So when we're building this mystery isotope, we know that the atomic number is going to add to 1 to equal 37, meaning that our atomic number will be 36. In the same vein, the mass number will add to 0 to equal 77. So the mass number will remain 77. When we try to figure out what the element symbol is here to complete the question, we go back to the periodic table. We look for the element that has an atomic number of 36, and we get, this looks like krypton right there. Krypton, which has an element symbol of Kr, and so the answer is krypton 77. Okay, let's try one more just like this one. We have an isotope of phosphorus 29. Phosphorus has an atomic number of 15, and it produces silicon 29. And here's the twist, an unknown nuclear radiation. So this time, for the first time in the entire video, we are solving for the nuclear radiation instead of the element or isotope. So we have to think backwards a little bit. We have to first observe what's happening with the atomic numbers. That's always where we start. 15 changed to 14. That means that there was a -1 happening. 15 minus 1 equals 14. So we know that the atomic number is -1. 29 didn't change at all. It stayed 29. So we know that this was a +0, meaning the mass number is 0. Can you guess what nuclear radiation this is? That's right. This is a beta particle. So, phosphorus 29 results in silicon 29 and emits a beta particle. I really like this question, so we are gonna do one more similar to it. This time, we have a mystery product which reacts to form this, I think it's like uranium or something along those lines. Uranium 90, I can check. 90, 90, 90. Sorry, 39. Yerium. Okay, here it is. So it reacts to form yerium-90 and what appears to be a beta particle, right? So now we need to find the product, right? So I'm thinking 39 and -1. When you add these things together, what do you get? Well, you're actually subtracting here. You're doing 39 plus -1, which is giving you 39 minus 1, or 38. So I'm thinking the atomic number must be 38. Same thing, when we look at our atomic numbers, 90 plus 0 is 90, so the mass number is 90. Well, let's put our brains together and think, what element has an atomic number of 38? Let's look, and it is strontium. So the reactant for this nuclear equation was strontium, and strontium reacts to form these two products. All right, I hope you guys enjoyed this video. As always, if you have any questions, make sure to leave them in the comments below and someone from our team will answer them. And we hope that you are following along through the chemistry playlist and learning so much. And as always, subscribe, make sure you're ready for the next chemistry video that we release, and check through the playlist to see if there's any videos that you missed that can help you. All right, see you guys next time.